Welcome everyone to our May seminar. The topic of today's seminar is opportunities for geothermal and thermochemical energy. My name is Dr. Andy Smallbone. I'm an associate professor at Durham and I'm the director of the Network Plus. This event is organised through that same Network Plus, which is the network for the decarbonisation of heating and cooling, and is a part of its monthly series looking at different challenges of decarbonising heating and cooling. This month, we're delighted to welcome speakers from Newcastle and Nottingham universities who are leading research around geothermal opportunities and thermochemical energy storage. So we're welcome and we are very grateful to both presenters for presenting and providing their time today. So the first speaker will be Professor Manning, who's a geologist whose work focuses on how we can use the Earth's natural resources to support our population. And he is a chartered geologist and was president of the Geological Society of London from 2014 to 2016. So David's project is called NetZero GeoRDIE, and it addresses fundamental challenges in heat abstraction and storage, the engineering challenges of integrating geothermal into whole energy systems, as well as looking at regulatory and legal implications of closed loop systems and subsequent liabilities. So David, do you want to give us an overview of what your project's been up to, please?
Right, thanks very much, Andrew, and thanks everyone for turning up today on such a beautiful sunny day. So what I'm going to do is give a tip of the iceberg view of the project NetZero GeoRDIE. NetZero Geothermal Research for District Infrastructure Engineering is where that name came from. We were funded in the first round of the Decarbonising Heating and Cooling programme. And of course, it's a cast of many, many people. So we have myself, Mark Ireland, Mo Rainier, Sarah Walker, Yusuf Aghlaghi came and has moved on to other jobs. Tom Chardon's joined us. Mohammed Khalil was early on the project and then left, and Hui Ben is part of the project now. We have Ola Pedersen, who has now moved to Aarhus University, Anna McLean in law in Newcastle. And then in Glasgow, we have Joya Falcone. Sadly, Rob Westerway died at one point in the project. We've got Dave Banks, we've got Chris Brown and Isakolo as postdocs in Glasgow. We've got John Lewis from Durham, Rachel Brown and Sydney O'Brien have led on the making sure that everything works front of the project. So what is NetZero GeoRDIE? Let me just move on. We've got a range of partners in the Northeast in particular with an interest in geothermal energy. The project's revolving around the borehole that we have in Newcastle Science Central, as the site was originally called. And the point of the project is to look at how that borehole can be used to provide heat to the development on this 12-hectare site. The partners are all people who are involved, or companies who are involved one way or another with geothermal energy, particularly in this region, though of course companies like NG and Geon have a very wide geographical spread, and Schlumberger as well, of course. So the well that we have was built in the Newcastle Science Central borehole, which is a 2,000 deep borehole. The borehole was started in 2011 and completed in 2014 with the well. The well is the hole with this steel casing in, and you can see the perforations in the casing, which extends from about 1340 meters deep to 1640 meters deep. So it is an exceptionally deep borehole, and the well that's been built in it gives access to that depth of 1640 meters. It's on a city centre site, and just to give you an idea of the distance, the church there in the corner is about half as far away as the bottom of the well. And as you go down the well, you're going through a sequence of coal-bearing rocks. You've got the windsill, you've got the limestones, you've got the fell sandstone at the bottom of the well, which is what we were aiming for as our target. It was a major operation to deliver this piece of work, and that was all done before NetZero GeoRDIE was conceived as a project. The key in NetZero GeoRDIE, though, is to look at the research question of how can a hole of that type supply the energy needs of the modern building. And the point to bear in mind there is that the hole was bone dry. Having gone to the trouble of drilling a hole to 1600 meters into a sandstone, which one would normally think of as an aquifer, we found that there was no water in that rock and there was no way of getting any heat out. from natural processes of extracting fluid. So the idea then came along to look at having a downhole heat exchanger. So the graphic on the left here shows how that would work, with cold water going down the annulus of the well, coming back up a central pipe, circulating round through heat exchangers to satisfy the needs of a heat load. At the same time, since the well was created, the Urban Sciences building was put up next to the well, and this is a modern building, a brand new building effectively, where it is instrumented to within an inch of its life. We know very well what the heat demand is of this building, so it's ideally situated because it's only 20 meters away from this borehole. So to put the two together makes a lot of sense scientifically. And the process of what we're doing involves these three different angles: modeling, measurement, and management. And that then takes us through to the key questions here. From modeling, does the well heat, do the yields of heat from the well match demand of the building of that type? Then what are the building's requirements, and how will those change in response to climate change as we move forward? And then, equally important, what are the regulatory issues that might affect our ability to take advantage of this resource? And the whole point of this is that it will inform the design of combined heating and cooling schemes in a city centre environment. And this is an image of what the site is beginning to look like now, with these buildings now in the middle here existing, more being built, these not yet. And the borehole is just here, right in the middle of this patch of urban ground. So there are 6 areas effectively within the research plan, and they involve engagement. I'll talk about the first 5 in particular, this being an engagement event, effectively, talking to this audience. But the key thing here is that we've got a heavy front load of modelling the heat transport within the rock mass that's around the well, and then within the wellbore itself as a coupled system. Looking at the uncertainty that's involved in these models, especially as we're projecting forward into maybe the next 25 years, maybe 50 years for the life of a facility of this type. We also need to do experimental work to measure what the well can actually do with a thermal response test. And then to look at how the behavior of the well itself from those models and those measurements can be integrated into the heat network for the end users to be able to use it. And then really important to look at the regulatory and legal implications to see what framework this sits in and how it can be used. So I'll cover those 5 topics in the next 15 minutes. The modelling work for the first of these is being done in Glasgow, where they've developed a model based on a schematic of the borehole with that concept of cold water going down the outside, warm water coming up the inside of the well to the surface. And the finite difference models that they've been carrying out there have told us what the effect is on the heat thermal profile of the well. The point about this is to find out what the influence is adjacent to the well, how far away does the well actually cause cooling of the rock, and that helps us understand what the long-term behavior and performance of the well is from the point of view of actually extracting heat. So with this, with the modelling that's been done, the interesting thing that shows about this is in the top right-hand side in particular, you can see a set of graphs for different loads. You've got 50 kilowatt, 10 kilowatt, and 150 kilowatt of thermal load. And here the dashed line, the input water temperature, and the solid line, the output. And this is circulation, don't forget. So it's a closed system with the water circulating around through a heat exchanger. And clearly, the more heat you take out, the more rapidly the temperatures drop. So with the 50 kilowatt load, we reckon that that will last for, that's the one which will last best over a long period of time. So here we're looking at modelling over half a year in that particular example, but longer term modelling has shown that if we take this over a 20-year period, we're seeing, particularly with intermittent operation, where we might be heating in the winter and cooling in the summer, that we can look at we can project a life of 20 years with some drawdown, but maybe not enough to cause any problems. And that depends on a later work package to tell us what the building's needs are and how they will change over that period of time. The interesting thing about this as well is that we, having established that 50 kilowatts could be extracted over a 25-year period, we can see what effect that has on the temperature of the adjacent rock. And this animation happens very, very quickly. And you'll have seen that it started off as a very flat set of temperature contours parallel to the Earth's surface. And looking at this, it draws down very, very quickly in the initial years. And by the time you get into 10 years, and this is extrapolated here over a number of years in this animation, the key thing here is over 10 years, you've got this drawdown of temperature and a radius of thermal influence. So that's how far away from the hole do you have to go before you can have the same temperature as if the hole wasn't there. And that's about 40 meters at 161 meters depth. And it increases to about 60 meters at the bottom of the borehole heat exchanger because more heat is being extracted. So we can see that that varies with depth. I'll just move on to the next one. Looking at the uncertainty analysis, which is what we've been doing at Newcastle, we're doing this because when we first drilled the well, so Paul Younger and I put this hole down and wrote it up, and one of the papers in 2016, which was led by Paul, reported the thermal conductivity values. And you can see with depth, as we have so much variation in the geology as we go down, we get considerable variation in the thermal conductivity, almost by a factor of 2 for some of the values that are measured. And of course, the temperature that's measured varies immensely as we go down. So this means that these factors have to be taken into account in the models we've just been looking at. Uncertainty analysis tells us which of the parameters we need to focus on because that particular parameter has the greatest influence. And so again, using the same model and using the same heat load as Glasgow have used in their finite element models, we're using 50 kilowatts over 25 years. And we can see that having done a Monte Carlo simulation of the models over 1,000 simulations, we pick up what the dominant causes of uncertainty are. And it turns out that the ground thermal conductivity and heat capacity are rather important. Drilling down to that in a bit more detail, we can see overall the uncertainty and the sources of the uncertainty, or the main causes of uncertainty in the analysis. So the graphs on the right here show for the different factors that were in that table, which ones are the dominant sources of uncertainty. And the geothermal gradient is in the far right. The temperature here is clearly important, but that drops off. And the one which appears as we go through time, so we're going from a time of trivial amounts, a week to 25 years, and time axis on the XY plot down below, we can see that the geothermal gradient starts off as being the dominant factor in controlling uncertainty. But as time goes on, the thermal conductivity, this line labeled KS, gets more and more important. And so it suggests that we really need to understand that thermal conductivity of that composite pile of rocks, each with a different thermal conductivity value for each layer, if you like, in the cake. That needs to be well known in order to have a model with least uncertainty for forward projections into the period of 25 years. At the well itself, we plan to do thermal response tests, and this is something which we've been wanting to do ever since the project started, of course. The purpose of these thermal response tests is to measure how much heat can be recovered using a circulating fluid. That's the basic intention, which is effectively doing what the models want to have. The models are trying to predict how much heat can be recovered from the circulating fluid. So we need the measurements to be able to calibrate the models and to refine them and to improve them. But this is in procurement still. We haven't yet managed to establish a way of doing this for all sorts of good reasons. What we want to do is to have a system of this type where there'd be a thermal response test unit at the top, which might be delivering heat, or it might be delivering cold water down the well, a temperature sensor string to go down the well in the annulus to measure the temperature. The water would be circulating round in the same way, but we'd have fiber optics in the uprising part to get continuous temperature measurement with time and along the length of the heated water return. So that's the plan. And we're currently talking to a number of organisations which we hope will be able to induce into getting this test carried out. So that's a work in progress at the moment. When we look at the integration of what the well can do with the energy network, and we're looking at the behaviour of the urban science building, this is work being done in the School of Engineering at Newcastle. As I say, we've got a building here which we know very, very well. It's got a lot of monitoring, and we've got very good high-resolution temporal data for the needs of the building in terms of what its heat load is. There's a gas boiler system, there's a heat exchange system which we could, in theory, tap into, but at the moment, the main focus is on the demand of heat for the building and looking at scenarios of how that changes over time with climate change. So the existing demand is shown in a graph of this type, and you can see that over a period of time in a year that we have a series of spikes and troughs, peaks and troughs as we go along. We can see the maximum half-hourly load, we can see the average load, and we can see the model load in green here. So we can see we can predict that pretty well in the first pass of the predictive work. As we move on to look at the future, then this has been looking at the existing load and using a deep learning model. We've tried to extend from 2020, which was used for training purposes, through to what we go back in 2080. The heat load, as you can see here, the blue cloud spots is in 2020, and it's a very broad cloud, whereas in 2080, it has condensed a bit. And this is reflecting the reduced need for more heat at particular times. So the heat load is on the y-axis here, and we're seeing overall the demand for heat decreasing in response to climate change by the time we get to 2080. And that gives us a maximum predicted heating load of 784.82 kilowatt hours for 2020, dropping down to 715.70 precisely for 2080. Then the bottom graph here shows the required cooling load, and this does the opposite. So you can see here the cloud of green points here is for 2080, and the brownish points are for 2020. And you can see here that the demand for cooling has increased. And in this case, it's moved up from 0.75 megawatt hours, which is about 750 kilowatt hours in 2020, to 1.23 megawatt hours in 2080. So you can see there's a big change there. And this is then the challenge that well has to meet, either taking that heat or providing the heat for cooling in the winter. So with the thermal demand, again, looking at the modelling of thermal demand over a year, we've again used these artificial intelligence methods with deep learning models to test different approaches to understanding which best predicts the load, and that has boiled down to selection of the long short-term memory deep learning models and the random forest machine learning model for giving the best predictions. Using this approach, we're conscious that the building load is dynamic, and so we can compare the requirements of the building for a fluctuation between demand in the summer, which is low, and demand in the winter, which is high. And you can see that if we assume, for example, constant load, we get these orange curves where obviously the system is losing temperature, the well is getting to a lower and lower temperature as time goes on. So in 5 years, it is at its lowest temperature. But with the fluctuating load, of course, that gives the well a bit of a rest. And so you end up with a slower reduction in temperature. And so the longevity of the resource has increased. And the idea behind this is then to model the coupling of that well when we know exactly what the TRT tests give us in terms of measurements to what the building actually needs, and a number of ways in which that can be done, depending on the permutations of borehole heat exchangers and heat pump systems, which then take the water into the building. So that's helping us understand the borehole, all of that work now, looking at what the demand is for the building now, how that might develop in the future, how the borehole behaves under dynamic load and how we can predict that, and then to build a coupled system where we understand the combination of the borehole and the building as a coupled unit. Now, that's all very well, but of course the regulatory and legal questions are absolutely paramount in this. And one of the interesting things here, of course, is that the regulation of heat extraction falls into a number of different areas of regulation and legal activity. We've got environmental regulation, we've got planning permission, we've got the law relating to tort as well that we need to pay attention to. So we've been at Newcastle, we've been looking at this with Anna McLean doing the work on this, starting off with the environmental side of things, with the water abstraction to take the hot water out. Then we're looking at the Water Resources Act, and there's potential for this to prevent reduction in the groundwater temperature, but that relates to open loop systems, not closed loop systems, which we have circulation in, because we're not taking water out of the system. With the environmental discharge permit, we've got the ability here to look at heat discharge following reforms, but not extraction. So that's not quite mapping onto what the requirement is for the system. We look at planning permission. The Town and Country Planning Act is one where we might ask the question if heat extraction is a planning matter in the way that extraction of other materials is a planning matter. So that's an area which needs clarification. And then for the tort law, then there's the issue of nuisance. There's the question of competing property rights. So if we have a well and our neighbour puts a well in, are we stealing someone else's heat? And is heat a property that could be dealt with in the same way that other property is considered? The licensing regime for heat, again, Anna's come up with question marks here. We've got some similarities to oil and gas licensing, but there is this big question of who actually owns the heat that's beneath the ground. And I think that's something which there will be opinions about, but we don't know the answer to that question yet. With the water abstraction licensing regulations, looking at how they might fit, again, we've got issues there with the way in which the heat is extracted and how that can be adapted, how that can fit within the Water Resources Act 1991. So the conclusion is that that the legal issues are complicated with a range of legal regimes, a lack of comprehensive regulation. So this is a fairly fast-moving field, but one of the possible solutions is to think of a licensing regime for heat, which takes into account issues such as the ownership of that heat and the ability to guarantee access to heat. Because if you have a well and you're producing heat out of it and it is a source of heat for a building, you're depending on that source of heat, you have to be able to guarantee access to that heat. Access not just from a scientific and technical point of view, but access from a legal point of view as well. So overall, this program NetZero GeoRDIE is providing a detailed evaluation of how this system might work in an urban setting, and it's got a number of angles to it, as you have seen, which each of which is the tip of an iceberg that would each take half an hour's talk to present to you. We've got the integration of demand, that is the engineering demand rather than the demand of people. Well, ultimately that goes into the engineering demand for heating and cooling, and how the borehole and a well within that borehole can then provide that. We've highlighted some of the regulatory issues. There's still quite a way to go on that. But the whole point of this project is that we want it to de-risk future projects. So with that, just to put it into context, the point about the Newcastle well is that it is unique. There's no other city in the country which has a well 1,640 meters deep that can be used for geothermal research. So that makes it extremely special and an asset that Newcastle has as a city that could be taken forward. Just to put that into context, and here's a bit of a plug because part of my activity is a senior science user for the UK Geoenergy Observatories. We have two facilities funded by NERC and delivered by BGS. One in Glasgow, which is in coal mine geothermal system in the centre of Glasgow, and one in Thornton near Chester, which is a shallow aquifer geothermal system in Perma-Triassic sandstones. They both go to 100 meters deep. And although they can do fantastic things, and I commend them to you, the point is that they will not go deeper than 100 meters. So if we want to go for deep geothermal, Newcastle is the only borehole and well in the public domain which is able to do this. So with that, I will finish. I hope I've given you enough information to show the promise that we'll be able to inform city centre heating and cooling schemes. And if need be, please contact me at the email address here. So thank you.
Thank you, David. Thank you very much.